University of California, Riverside, and my research interests are in optimizing the irrigation water use in landscape and agricultural system through the use of data-driven cutting-edge technologies. In today, I'll present some challenges, opportunities, and workflow of using drones for irrigation management. Here is the outline for the presentation. I'll start with some background regarding the importance of irrigation management in agriculture, which Dr. Montazer and Dr. Hagverdi had presented in more detail. I'll then followed by the application and types of drones, some flight regulation we should keep in mind when flying a drone, and the process of data collection using drone, important vegetation indices, their interpretation, and then at the end, I will conclude with the major takeaway. The importance of agricultural water management is more than ever before. The demand for food is increasing, and the demand for food is increasing with the increase in global population. One of the major inputs for crop production is irrigated water, which makes agriculture the major consumer of available water resources. And the need of water for agriculture irrigation is increasing as we have to produce more food to feed the growing population. Therefore, there is a need of agricultural water management. In California, which is a home to major agricultural production, on average, we irrigate 9 million acres of land and use about 34 million acre-foot of water. And this is a lot of water. Though the demand for irrigation water keeps increasing, water availability is being decreased because of various factors, including climate change. Therefore, there is a need for efficient irrigation management in agriculture, which in turn may help us to use less water without sacrificing the yield potential. The site-specific irrigation management, which Dr. Hagverdi explained in detail in the earlier presentation, and which is the application of water only in the region of need, can help us to optimize the water use. And for this site-specific irrigation management, drones with various sensors can be used to monitor the field, map the field, and identify the region of water stress in the real time. Okay, what is drone? Unmanned aerial vehicles, which are commonly referred to as drones, are remotely controlled aircraft that might be equipped with various components, including GPS and sensors or cameras. And drone help us to scout the field in real time to detect the abiotic and biotic stresses in the field. And based on the type of the sensors we fly with the drone, we will get different drone images, which will help us to identify the region of water stress or any other biotic and abiotic stress in our field. This figure outlines the problem because of changing climate and the ways drones can be used for efficient irrigation management to improve food and water security. Some of the major problems we are facing are water scarcity, increased rates of evapotranspiration, decreased production, and degraded soils. And to address these problems for improved agricultural water management, drones can be used in various ways. And in next few slides, I will be explaining the application of drones. Among many different applications of drones in agriculture, some of them are presented here. Drones can be used to map the variability in the agricultural field. Drone provides real-time high-resolution imagery, which will help in decision-making and in delineating management zones for site-specific applications. The image in the right is an example of a field delineated into 4 zones based on the colors. for a site-specific application of the agricultural inputs. And similarly, drone images can also be used to detect water stress in plants, which can either be abiotic or biotic stress. And detection of stress region in the field will help us to make an informed decision for irrigation scheduling or the application of other agricultural inputs. And through the use of high-resolution drone imagery, we will also be able to predict the crop biomass or crop yield with acceptable accuracy before the harvest. So these are some of the applications of using the drones. So far, we learned the importance of irrigation management, applications of the drones or their roles in agricultural management. And in next few slides, I'll present the types of drones and some of the sensors that are used in agriculture. Mostly there are three types of drones, namely fixed wing, rotary wing, and the hybrid. The first two are the major types of drones used in agriculture. Fixed wing have rigid wings and are able to glide in the flight, and they are known for their long battery life, which helps to cover the larger lands. And the rotary wing can be either quadcopter as shown in the figure with 4 blades, or can be hexacopter with 6 rotors. They're relatively easy to operate and allows for vertical takeoff, hovering, and closer crop inspection. The last one, the hybrid, allows us for vertical takeoff like a rotary drone, and then transition into a glide flight. Okay, once we have our drone of interest, we also need to get a sensor to mount on a drone. Sensor selection is primarily based on our objective, and depending on our need, we are getting different types of sensors. For example, RGB camera, the one mounted on a 3DR drone on the top left, is a natural color or true color camera. Images from these RGB cameras will look similar to what we see through our eyes. The picture in the bottom left is an example field captured using an RGB camera. They are most common and used in field scouting. A camera on the top right is the multi-spectral camera from MicaSense. A multi-spectral camera can detect the lights which are not visible to our eyes. For example, red edge and near infrared bands. And these bands are not visible with our eyes. However, they are important as they help us to detect plant health and the stress in the plants. Because healthier plants will have stronger reflectance in the near infrared region than in the RGB red, green, blue region. And we will discuss various vegetation indices that can be computed using this multispectral camera later in this presentation. Other sensors which we can mount on the drone is the thermal camera, the one presented at the bottom left, and it detects the radiation in the long wavelength infrared region, and it helps us to detect water stress in the plants. And the image on the top left is an example of the field obtained using a thermal camera. Another example of sensor is a LiDAR, also called a light detection and ranging. It measures the distance between the sensor and the object, and it is widely used in terrain mapping. So we know the type of the drones and different types of sensor that we can use in the drone, but to be eligible to fly a drone, we need to have a drone pilot license, for which we need to pass a Part 107 test. There are a number of regulations administered by Federal Aviation Administration, FAA, which we need to follow before flying a drone. What I'm presenting here are some basics, and it should not be taken as a complete guide, nor should be considered as a permission to fly a drone. Some major numbers that we should keep in mind when we are ready to fly a drone are, for example, the number of drone we can fly simultaneously is 1. The fastest we can fly is 100 miles per hour. And the maximum height we can fly a drone is 400 feet above the ground level. And our drones should not be more than 55 pounds, including all the components, example, sensors and the cameras. And in case if we crash our drone, then we have to report that to the FAA within 10 days. And the minimum age to take part in this part 107 certification is 16 years. So, and there are a few other numbers that we need to consider. And in next slide, I'll provide a link which provide a detailed information from the FAA and the ways to get the FAA license. When you appear for a test, you will get the questions from different categories, including regulations, airspace, weather and data, loading and performance of the drone, and various emergencies and maintenance things that we have to keep in mind when flying a drone. So before you go for the test, we should be ready or well prepared in all these aspects. And a link here is, we can find it online from FAA, and it provides all the information and available resources to get prepared for the part 107 exam. Okay, once we have our drone, camera or sensors, flight permission, and drone pilot license, there are some basic steps we should follow. In next few slides, I will explain briefly in these steps which we need to consider when flying a drone. The first one is mission planning. Planning the mission flight in advance help us to get ready and to estimate the flight time. There are various applications that can be used to plan a mission flight. For example, fixed 4D capture, drone deploy, DJI pilot, etc. And they are available to download in our smartphones. On the right is the image from Pix4D capture. Here you can see that we are setting a flight mission. The area with the green sets shows our area of interest, and the white transect, the white lines are the path of the flight. The blue arrows shows the blue arrow is highlighting the flight altitude. That is we are flying our drone 130 feet above the ground level. Also above that, there is a ground sampling distance values for this drone flight. On the bottom, it shows, on the bottom of the right arrow, it shows the area we are flying, 157 times 459 feet area, and the time the drone will take to complete this mission, to complete this flight, is 10 minutes and 3 seconds. Once we connect the drone, it will show a pop-up message in case. So these are case specific, like depending upon the application, these things might be different, but I'm currently referring to the Pix4D capture. And so once you connect the drone, it will show a pop-up message indicating the area covered, the altitude of the flight, and the flight speed. The time of the flight depend on all these settings, including the frontal and side overlapping of the images, altitude of the flight, and the area coverage. The next step is to conduct the drone flight. Once we finish planning the mission, we then fly the drone. However, there are things we need to take care of or be aware of when flying a drone. We should fly a drone on a clear day. We should not be flying a drone if it is too windy. We should not be flying a drone above 400 feet ground level, we should consider the drone speed. If it is too hard, then we may have a problem with batteries. We need to figure out if we need extra batteries or calibration panel to calibrate the camera, or we might need a ground control point for precise georeferencing. So before we are ready to fly our drone, we have to check a long list of the checklist to go to the field so that we can have effective data collection. Data management is also an important part of the drone flight. Once we finish flying a drone, we have to copy and make a backup of the image we obtained from the flight for the further processing. Depending upon the area covered by the drone flight, we may receive hundreds of images. Therefore, individual images obtained from the drone flight should be stitched together to get field maps that cover the area of interest. Again, there are various software which we can use, for example, Pix4D Mapper and ArcGIS Pro to stitch the images we get from the drone. Another important part of drone flight is to calculate the vegetation indices that make sense of the data we are collecting or we collected. And depending upon the type of sensor we use, we can compute various vegetation indices that are related to plant health and water stress. So over here, I'm presenting the most commonly used vegetation index to access the plant health and growth. So the number one is Normalized Difference Vegetation Index. It is used to quantify vegetation greenness, which helps to understand vegetation density and plant health. When our Ndvi value is close to 1, then the vegetation is dense and healthy. Another one is the Green Normalized Difference Vegetation Index, which is the ratio of difference between near infrared and the green bands. The GNDVI helps to estimate photosynthetic activity to determine water and nitrogen uptake in the plant's canopy. Solar Adjusted Vegetation Index, SAVI, is also used to correct NDVI for the influence of soil brightness in the areas where vegetation cover is low. And SAVI is calculated as a ratio of red and near infrared values and consider the soil brightness correction factor. These are just some of the many different vegetation indices we can calculate using the drone images. There are so many different vegetation indices we can calculate depending on our need, just using the same images we capture from the multi-spectral camera. So once we have our vegetation indices, the next step is to prepare the field map and store it for the future reference so that we can take the field map with us when we are in the field. The last one, ground truth and take action. So we can, by observing the processed map, we can identify the area of stress in the field. We can then go to the field and validate the findings and make a decision accordingly. Okay, pointer option is a pointer. Okay, so far we have learned the importance of remote sensing data and ways to acquire drone images and their processing. Once we have the processed image, like shown in the slide, we need to understand it. Here, I'm presenting an Ndvi map obtained from the alfalfa field. Ndvi, again, is the common vegetation index that describes the growth and health of the plants. A value closer to 1 indicates the plant is healthy and dense. So in the map, we can see patches of 5 different colors ranging from red to green. Here on the top, we have a small red patch, which has Ndvi values less than or equal to 0.2. So what does it mean is it might be a surface where plant density is less and the earth surface is exposed. On the bottom, we have a big patch of orange color, and it says the Ndvi value is less than or equal to 0.4, which means the plant density and growth, is not optimum. Plants might be stressed in this region. We have many different green regions over here, which have a NDVI value of more than 0.8, which means the canopy growth in the green regions is healthy, or the plants in the green region are healthy and they have a dense canopy. So this is how we read the processed map and make an informed decision for site-specific application of agricultural input. So if you go in a field with this map and see something like this, so you may want to see, so some of your sprinklers might be broken in this region, so they might not be irrigating if it is the case of water stress, or some of them have some biotic stress from pathogens. So this will be very helpful in scouting the field and in determining or in making a decision for site-specific application of agricultural inputs.
Anish, you may want to perhaps skip this so we speed up and stay on schedule because we are running behind.
Okay, so this was the last slide for the example. Again, I'm presenting here the NDVI map from one of the agricultural field, experimental field we have in the riverside. Over here, I wanted to show like the green regions are healthy. And again, the red regions with small patches of red regions and white surface shows that the plants in these plots are not growing properly. They are not at full canopy. So so this is the last slide for the presentation. So there are many challenges and opportunities of using drones in agricultural water management. Some of the opportunities we have are by using a drone, we will have real-time evaluation of the field, evaluation of plant health and growth of the plants, decision-making and irrigation scheduling, and drone also helps us in predicting the yield before we harvest. However, there is a challenge in flying a drone. We have to know various technical aspects of drone, image collection, processing, and interpretation. But if we follow all these steps and be able to get the representative images of the field, explaining what is going in the field, then those data would be very helpful for making a decision of site-specific application. These are some of the references I used for the presentation. I would like to thank UC Global Food Initiative Fellowship for the student fellowship and the USDA NIFA for funding the project. Now, with this, I would like to thank for your patience. If you have any questions, please feel free to email us.